So let me please introduce our speaker today, Pratik Saute. Please come on the line. He is a postdoc at Los Alamos National Laboratory. He has considerable experience in condensed matter physics and quantum computation. His work includes developing theoretical and computational approaches at the intersection of condensed matter physics and quantum computation. Pratik also works utilizing HPC systems and DWave's quantum annealing computer to understand properties of exotic magnetic materials. Pratik is a member of a team to advance research in cutting-edge technologies for Los Alamos National Lab and has a PhD in physics from UCLA. I will also introduce, as I said, two of Pratik's colleagues will be panelists today, which means they'll be standing by to answer questions during Pratik's talk. The first is Cristiano Nizzoli, a scientist at Los Alamos National Lab and a senior co-author of the paper that Pratik will be telling us about. In addition, Francesco Caravelli, who was formerly with Los Alamos and is now associated with the University of Pisa. So welcome, Pratik, and our panelists, and you can get started.
Excellent. Okay, so thanks everyone for taking the time to attend this talk, and also to DWave for the wonderful opportunity to present our work. I'm going to talk about a line of research that is slightly different from two of the more prominent applications of quantum annealing, which are optimization and simulation of quantum materials. So this talk is going to be primarily focused on essentially how one can simulate and study classical as opposed to quantum magnetic materials using a quantum annealer. And as I will show below, we have had decent success with this task. And the material presented in this talk is also available on archive at this number. Please take a note of it if you are interested, and I encourage you to look at it for more details. And looking at the previous webinars from DWave, I will assume that the audience is primarily familiar with optimization and perhaps not so much with statistical physics. So I will aim to provide a high-level picture of each of the important aspects of the problem that we want to solve and also our approach. So as Susan mentioned, this was done in collaboration with a few other people, and this work wouldn't have been possible without them. So my collaborators include Andrew King from DWave and 4 staff scientists from Los Alamos, including Susan Minevsky, Carlton Coffrin, Cristiano Nizzoli, and Francesco Caravelli. And Cristiano and Francesco are attending and will be answering questions and might show up at the end as well. Okay, so let's get started. So here's a quick outline of the talk. So the talk is going to be a marriage of 2 different facts. The first one is that a quantum annealer generates samples from the so-called Boltzmann distribution in the slow anneal regime. And the second one is that this type of sampling is useful to numerically study the properties of classical magnetic materials. So I will first talk about these 2 things. Next, I will talk about the piled up dominoes model. So we believe that the approach I'm going to propose in this talk will actually apply to a broad range of models and not just to 1 or 2 specific models. But to demonstrate the utility of this approach, we want to make sure that the output we get from a quantum annealer really does match what the material's properties actually are. So we chose this model called the piled up dominoes model. It has an exact solution and we know its phase diagram. So I will talk about this after discussing the background. And next I will move on to the results that we got using quantum annealers. So I will show that we have had reasonable success in mapping out the phase diagram of this particular model. And we have also had a decent success in getting the critical exponents and identifying the boundaries between the different phases. At the end, I will discuss a phenomenon called critical slowing down. And this really tells you why quantum annealing has good potential to maybe outperform or maybe assist classical computing methods for the same problem. So there is a problem called critical slowing down, which is very prominent with classical approaches, primarily Monte Carlo simulations. And this problem doesn't seem to occur with quantum annealing, which is why this method could be advantageous in the future. So let's start with the first part of the background, which is Boltzmann sampling. So this is basically a property of the samples that are generated by quantum annealers. So just a quick recap, because maybe a lot of the audience is more familiar with optimization. So the primary application of DWave's quantum annealers is to solve optimization problems. So many of them can be mapped onto the so-called Kubo or quadratic unconstrained binary optimization form. So here the problem is essentially defined on a weighted graph with weights Jij's and Hi's. And the objective function, which we want to minimize, is a quadratic function of binary variables Si's that sit on each of the nodes of the graph. The goal is to find an assignment of Si's that minimizes the objective function, and we will also refer to it as energy for reasons that will become clear in a few minutes. So while the binary variables take values 0 or 1, the problem can be also stated in terms of SIs taking values +1 and -1, and it will be more convenient to use that convention as we go ahead. Okay, so to solve such a problem using a quantum annealer, you first map this problem or embed it onto the DWave's QPU connectivity, and you program the device and you get back samples, and hopefully the samples that you get correspond to the least value of the energy or the optimization or the objective function. So how is this connected to physics? So the idea, first step is to think of E as the energy of a configuration. So in the case of a classical magnetic material, such a function can actually tell you some properties of the material you want to study. So for example, consider a single 1D ferromagnetic material. A ferromagnetic material has the property that nearby spins like to point in the same direction. And this can be encoded by an objective function, which we will also call Hamiltonian, of this form. So you can clearly see that H will be minimized if every two neighboring spins point in the same direction because they get a minus sign. So you can code up properties of ferromagnetic or antiferromagnetic materials in a Hamiltonian. So it follows immediately, at least for this case, that the optimal solution or the two ground states of this problem will be those that have all spins pointing in the same direction. That can be all up as shown in the figure or all down, which is not shown here. So as we will see below, the ground state really captures, or the optimal solution really captures what happens at absolute zero temperature. And the Boltzmann distribution, which is going to be the meat of this talk, really tells you what happens at finite and non-zero temperatures. So let's go to the next slide. And how does Boltzmann sampling occur in a quantum annealer? So ideally, from an optimization perspective at least, the annealer should return to you a configuration that corresponds to the least energy or the least value of the objective function. So it should return the optimal solution with a probability of 1. So if you did one anneal with one measurement, ideally the output is really the optimal solution. But as you may have figured out after trying out such a thing on the quantum annealer, in reality what you get are mostly approximate solutions, so approximate optimization solutions, and sometimes you do get the optimal solution. And the other aspect is that the outcomes are probabilistic and random. So every shot could be different and you could be getting different measurement outcomes each time. Nonetheless, there is structure to this randomness. So the sample probabilities match the so-called Boltzmann distribution, and this has been found after a lot of systematic study of the outputs that you get from in the slow anneal regime. So what is this probability distribution really? So the probability of any spin configuration to occur is proportional to the exponential of the negative of the energy of that configuration multiplied by a constant called beta, which we'll get to in a second. And here z in the denominator is just a normalization factor. It's called the partition function in physics. And it makes sure that the sum of all probabilities is equal to 1. So what does this look like? So here's a schematic. So let's say the energy levels of the problem that you are interested in are E0, E1, E2, and so on, arranged in an ascending order. And if you just plug in the values of E0, E1, whatever they might be, you will notice that the highest probability of sampling will correspond to the lowest energy. And and the lower and larger energies have less and less probabilities of getting sampled. So how is this relevant to physics? So we just saw that Boltzmann sampling occurs with the samples you get from DWave. How is this relevant to physics? So the key point here is that such a distribution really describes objects at thermal equilibrium. And for magnetic materials described by an Ising model of the kind that DWave is able to optimize, the probability is really the same as the formula I showed you on the previous slide. Beta is just replaced by 1 upon kBt. Kb is a constant called the Boltzmann constant. It's a fundamental constant in physics. And T is the temperature. So before proceeding, let me emphasize here that the magnetic material models that we will be considering in this talk are purely classical, meaning there is nothing quantum mechanical about the model. So the Ising model that we just discussed a few slides ago is entirely classical. There are no non-commuting operators in the Hamiltonian, and the energy of each configuration is simply obtained by taking products and sums of real numbers. So there is actually a similar quantum mechanical distribution, similar to this one, but we will not be considering such a distribution in this talk. So we'll be using a quantum annealer to solve a purely classical problem. That's the summary. Okay, so to get an intuitive feeling of what the Boltzmann distribution would look like in a few different cases, consider two extremes. So let's say your material is at a really low temperature, and let's say the temperature tends to zero, then beta is really large. And you will find that basically all the samples or all the material is actually going to be almost always in the ground energy configuration or configurations. And with very low probability, you will see higher energy configurations. On the other hand, if the temperature is really large, then there's going to be a decent probability of the system being in any of the configurations. And at t equal to infinity, actually, the probability of being in any configuration is going to be equal. So just coming back to DWave's QPUs, from an optimization perspective, you want this one. You want the samples to correspond to a low temperature or the left-hand side, and not this one, because then you will be getting a lot of bad solutions. So if you care about optimization, you ideally want to cool down the QPU to really low temperatures. But the sampling temperature also depends on a few other factors, which you can control as customers, and that's what we found because we didn't have control of the QPU temperature at Los Alamos. So you can change the sampling temperature by optimizing the anneal schedule or the anneal time and also the energy scale. And there have been lots of studies to figure out the best set of combinations for this. Okay, so before trying to use Boltzmann sampling for understanding materials, I just want to quickly talk about why this happens at all. So why is it that the samples you get from quantum annealers are distributed according to this fashion? So there are a lot of details here, but I'm going to try to focus on providing a high-level approximate explanation. So recall that in quantum annealing, the qubits experience a time-dependent and changing Hamiltonian that starts with a Hamiltonian hx at t equal to 0 and ends up in this hz or the problem Hamiltonian or the problem that will describe our material for the purposes of this talk. And a measurement is done at the end here. So ideally, the system should evolve purely following the Schrodinger's equation with this Hamiltonian. But the qubits are not isolated. They're interacting with the environment they're embedded in. And the amount of influence the environment has on the evolution of the quantum state depends on how fast you do this anneal. So it depends on the anneal time primarily. So so when annealing is done really fast, such as in the fast anneal regime, the environmental interactions have been found to have a negligible effect. And this is called the coherent regime. So if you're familiar with some of the papers that came out from DWave, the Kibble-Zurich scaling papers from the last couple of years, as well as the science paper from 2025, they were all operating in this regime. And the samples generated in this case are typically not from a Boltzmann distribution. And really if one wants to figure out the actual sample distribution, it really requires a full quantum mechanical treatment of the problem. So this is not the regime that I'm going to talk about. So if you, on the other hand, look at the slow anneal regime in which the anneal time is greater than 0.5 microseconds, then then the environment has plenty of time to interact with the qubits. And in this regime, at a very high level, what we find is that the qubits are at thermal equilibrium throughout the anneal. So as you change the time, the qubits are really at thermal equilibrium throughout at a crude level. There are some details which I'm going to skip. So it follows that if you measure at the end here, the qubits are going to be at thermal equilibrium with respect to Hz. And as we just discussed, a Boltzmann distribution really tells you what happens at equilibrium. So a really crude analogy for our purposes would be the following. If the qubits are like ice cream, then fast annealing corresponds to a time scale of a few minutes. So if you eat ice cream within a few minutes, it really has the properties of an ice cream. But slow annealing, in some sense, corresponds to something like an hour with an ice cream. So if you wait that long, the ice cream will really have melted and it would be at room temperature and you would be drinking a liquid and not an ice cream. So in some sense, increasing the annealing time chips off or erodes some of the quantumness, and that may or may not be beneficial depending on your application. So for our application, we really care about the qubits being at thermal equilibrium. So we want slow annealing. Okay. So one important question here is, if you are working in this regime, what is it good for? It turns out that there are a few different applications. I'm only showing a few of them here, and there are lots of papers. So one of the applications that was proposed was machine learning. And it was shown that using samples from a quantum or classical Boltzmann distribution can be helpful for machine learning. Another prong was to generate samples for a quantumizing model. And there have been a bunch of papers to study quantum magnetic materials using this approach, using this fact. And it's also called quantum evolution Monte Carlo for those of you who are really interested in this. So there have been a few challenges with this type of an approach. So the quality of sampling has been scrutinized to a great degree over the last decade, and various studies didn't always agree. But recently, there have been a bunch of papers that came out of Los Alamos, and it was found that there is actually a sweet spot. There is a range of parameters at which the sampling quality from DWave is really close to a Boltzmann distribution, and in other cases there are variations. Now, so all of this is really promising, but if you want to use a quantum annealer to study a magnetic material, there is one ingredient that you really require. You want to be able to control the temperature of the sampling. And one straightforward way is to change the QPU refrigerator temperature. But if you don't have access, what do you do? So we used a smart trick. And the idea is that the temperature of the samples that you get from DWave are proportional to the inverse of the energy scale, which I'll get to in a second. And there have been a bunch of different studies that either assumed this relationship or verified or indeed verified this relationship, but usually restricted to small system sizes. So we were not really sure if we could use this for our study, but it turned out that it does a good job. So let's just quickly look at what this relationship is. And this relationship is really simple. And once you see it, it almost sounds trivial. So let's assume a simple model for a quantum annealer. And again, only in the slow anneal regime. So you put in H input. So this is the Hamiltonian you put into the program and send it off to the cloud. And let's say that the samples that are returned really come from this probability distribution. So probability of a configuration is proportional to exponential of negative of the energy with some factor, beta sampler, which we don't know. And it's also a bit hard to estimate this for big system sizes. But let's just assume this as a good model that describes what happens with the samples that you get. Now, suppose you are actually interested in studying a particular Hamiltonian, let's call it H. Then to access different temperatures, what you could do is just scale h. So put h input equal to j, which is just a real number, multiplied by h. And what will you get? So beta sampler will remain as is, but j will come with a factor of j, sorry, h will come with a factor of j. And you can actually absorb it in the beta term. So you get beta effective is proportional to J, or temperature of the sampling that you get is proportional to J inverse. So it's a really simple relationship. And it turns out we can use this to tune the temperature in our simulations. Okay, so by now, I think hopefully people are at least kind of convinced that there is potential to simulate a classical magnetic material using, at thermal equilibrium, using a quantum annealer. Now, we also saw that we have this secret temperature knob in the form of the energy scale of the input Hamiltonian. And there are a bunch of different properties we could study. But the most obvious and interesting ones for our purposes is going to be to understand phase transitions in a model of this type. So let's just do a quick summary. So uh, let's just look at at a simple example of phase transitions. So this is something we are all familiar with. I just took this from Wikipedia. So this is the phase diagram of water. The vertical axis tells you the temperature, and the horizontal axis is the temperature. Sorry, the vertical is pressure, horizontal is temperature, and we really operate at 1 atmosphere. So we move along this line. And if you at 0 degrees and at 100 degrees, water undergoes phase transitions. So there are similar phase diagrams for magnetic materials. So you can have a material that goes from ferromagnetic to antiferromagnetic to something else. And the phase diagram really depends on the model that you're looking at. What we want to do is to come up with a similar type of a figure for a magnetic material. And we are going to use a quantum annealer for that purpose. Okay, so we will pay particular attention to a few different features of a phase diagram of this type. So we want to identify critical points or lines. These are the boundaries between two different phases. And because of something called universality, which occurs in statistical physics, we really also want to understand the so-called critical exponents. So these are interesting because models that are very different from each other can have virtually identical behavior at the critical points or at critical lines. And lots of such models can belong to a particular set, which we can call a universality class. And if you want to study a particularly difficult to study material, at the critical point, you could instead study a much simpler material in the same universality class. So we will want to identify the critical exponents that characterize such universality. Okay, so here's a quick summary of what we want to do with a quantum annealer. So first of all, we want to map out the phase diagram, just like the one for water, ice, and steam. A magnetic material can have various phases. So we'll want to be able to tune the temperature of the material and also some parameter, maybe an external magnetic field or whatever it might be. This is just a schematic. This doesn't really correspond to the phase diagram we'll actually get. And the second task that we want to do is to focus on, let's say, two different phases in the diagram and really identify in a principled way the locations of the phase boundaries or the critical points. And we will want to do this along both the directions. So at a fixed parameter, we want to be able to change the temperature, and for a fixed temperature, we want to tune the parameter and see the phase change. Okay. So let me, before getting to the results, let me mention that a lot of work has already been done as far as using quantum annealers is concerned with regards to materials. So critical exponents have been found in the past using a quantum annealer, but let me emphasize that a lot of this work really dealt with quantum models, not classical models. So some of these papers cited here, they extracted critical exponents in a very different manner. They looked at what happens if you really quickly cross one phase. Let's say you go from one side to another really quickly, then you see a certain type of behavior, and that behavior tells you something about critical point that you have crossed. So a lot of the papers in the past have been about this type of an objective. There have been some works that dealt with classical phase transitions. So, for example, this paper from 2018, which appeared in Science, um, but the part of the paper which dealt with classical phase transitions really didn't tune the temperature in the way that we did. So we are really doing something new here. And there also have been a few papers, especially this paper from PRX Quantum in 2020, where the ground state phase diagram of a model was studied. So this is a fairly well-known model, Shastri-Sutherland model. And at t equal to 0, meaning the optimal solution, the ground state phase diagram is known exactly. And some people were able to obtain this phase diagram using DWave. So the missing piece here is temperature, which we are going to be controlling really finely in our simulations. So which model should we study? Our proposal is that we can use the methodology to any model that one might be interested in. But to demonstrate that the idea is sound, we have to choose a good model as a benchmark. And we really chose two different criteria for this. So first of all, we should know the exact solution of the model. That kind of makes it less interesting from the point of view of simulation. But if you know the exact answer beforehand, then you can compare it against what you get from quantum annealers. And hopefully then the experimental observations will match the theoretical ones. And the second one is about geometrical frustration. So we want to have a model that in some sense has a tunable degree of difficulty. So there is a feature called geometric frustration, which typically increases the difficulty of solving an Ising model, especially in optimization. So spin glasses have frustration, and that kind of makes it a bit hard to find optimal solutions. That's typically the case, need not always be true. And it also makes the task of sampling from a Boltzmann distribution difficult. So to mimic such difficulty, we are going to use a model that has a tunable degree of frustration. So we actually have the perfect model for this. And it turns out it has not been studied since a long time, not just on a quantum annealer, but numerically as well. So this model is the so-called piled up dominoes model. Francesco called it on Sagar-Whelan model, which you will see is also a really good name. Let's just look at what this model is. And then we are going to look at the results we got using DWave. So this model interpolates between two limits that are perhaps very well known in statistical physics and condensed matter physics, but maybe not so much in optimization. So I'm going to show the model in detail. So this model has a parameter, and the interpolation parameter, it tunes from this model, 2D squarizing model, and another model known as Whelan's odd model. And both of them are really old. So let me emphasize that the first model was solved in 1944, so 81 years ago. And the second model is also really old. And it turns out that you can combine these models and get another exactly solvable model, which is called the PUD model, piled up dominoes model. So as I said, it's parameterized by some parameter S, and it is just a combination of these two different Hamiltonians, S times H Whelan and 1 minus S times H squarizing. So I want to take your attention to the figure on the right. So the graph is just a square lattice, a square grid, and each of the black dots here is a spin. Now, depending on the value of S, the values on the red columns will change, but the blue bonds are always 1. So the blue bonds are always ferromagnetic, so with a minus sign, so -1 times sigma z, and the red bonds, which correspond to alternating columns, they have a value of 1 minus 2s. So when s is equal to 0, blue and red both are 1. So basically, there's no distinction between blue and red. Everything is ferromagnetic. All neighboring spins like to align in the same direction. So in some sense, that is an easier problem. And the other limit, when s is equal to 1, the red bonds will become -1. So this means the red bonds will be anti-ferromagnetic. It will want to make the spins next to the red bond anti-parallel to each other, but the blue bonds will be ferromagnetic. And this is called frustration, because if you look at any square or any plaquette here, you will see that there is no spin configuration that can make all bonds happy. Okay, so the exact solution of this is well known. Um, So remember the symbol Z that I had shown before? It's called the partition function. And once you know what Z is, you know virtually everything about the model. So Z was found in this paper in 1979. And this really tells you what the critical temperature should be at each value of S. And it turned out that Francesco, who's in the audience and a co-author in this paper, he independently found another solution which exactly matches the one from 1979. So we have two different solutions. I mean, one solution obtained from two different ways. And the phase diagram has three different phases: ferromagnetic phase, an antiferromagnetic phase, and a paramagnetic phase. So in the ferromagnetic phase, all the spins line up in the same direction. In the antiferromagnetic phase, they have an alternating up down arrangement, and in the paramagnetic phase, it's just really random, and there is really no ordering in the spins. So what does this phase diagram mean really? It means that if the system size were to be infinite, and you were in any part of this yellow region, then all the spins would point in the same direction with probability 1, essentially. But these critical points are really this critical line and this one, they're really special. As you cross this line from any direction, there's a really drastic change in the behavior, and you go from being ferromagnetic to paramagnetic. Okay, so how do you reproduce such a phase diagram using a quantum annealer? So I'm quickly going to outline our procedure. So you choose a large enough system size. You embed or map it onto the QPU of your choice. You choose a grid of J inverse and S values. So really you have a grid of Hamiltonians. And for each point in this grid, you're going to send it to the quantum annealer. You are going to get back samples, and you're going to analyze the samples that you get. And you're really going to look at uh, two different quantities. So at each grid point, we will compute from the samples a quantity called average magnetization. So you just sum up the spins from every configuration and divide them by the number of spins. So this is a number that will go from 0 to 1. And another quantity that we'll be interested in is the antiferromagnetic order parameter, or the staggered magnetization. So you add a weight of +1 and -1 alternatingly on the spins that you get from the samples. And and something that is up down will have a value of 1 um, eh, with respect to this. This quantity will have a value of 1. So these two quantities are of interest. So we choose a system size, for example, something like a 6 by 6 torus. Then you map it onto the QPU of your choice. So all of the experiments we did were on the Advantage 2 prototype device, which I think is no longer available. It's instead been replaced by a better Advantage 2 system. But the previous one had about 1,000 qubits, 1,248 qubits. And I'm just showing here 6 embeddings that we had for a 12 by 12 toroidal system. And all of these are disjoint. So it's like doing 6 experiments when we send one instruction to the DWave QPU. Now, when we got this diagram, we were really happy. So on the left-hand side is the exact solution, and on the right-hand side are the average magnetization and the staggered magnetization plots. So if you look at this one, it's clear that there's a qualitative match between the rough boundary between the regions of magnetization 1 and magnetization 0 from the experiments. That really does match with what you would see from the theory. And similarly, if you look at the staggered magnetization, it really has a large value. So this should be 1. There's a mistake in the computation here. So just think of yellow as 1. So it's 1 in this region and 0 everywhere else. So we really got the qualitative phase diagram correct in our first attempt, which we were really happy with. And let me emphasize that as far as we know, this is the first time that a phase diagram which involved temperature changes was obtained in this manner, meaning an order parameter was plotted as a function of two different parameters, one of which was temperature. Okay, so we were already pretty happy with this, but then we decided to go a bit further. So let me briefly describe that challenge that we had. So this was for a 12 by 12 system size, which is fairly small from a statistical physics point of view. Imagine making the system size bigger and bigger, 100 by 100, 1000 by 1000, and so on. What you will actually see is that the boundary here, which is kind of fuzzy, is going to become more and more sharp. And in the limit of an infinite system size, it's going to be like a step function. You'll go from 1 to 0 immediately as you cross a particular boundary. So if you were able to do simulations of larger and larger system sizes, you would be able to see this. But because of the hardware connectivity and the size of the QPU that we had access to, the largest system size we went to was 12 by 12. So how do you still find out in a very principled manner how what the curve that divides this region from this region? So there is actually a way to do this. It's a very well-established technique called finite size scaling. So I'm going to talk about that in the next few slides. Okay. So our next objective is to identify critical exponents and to identify critical points which make up the two lines that separate the three phases. So to do that, we really found it important to do what is known as calibration refinement. So the point here is that even though your system has some symmetries, the system that you want to model, the abstract model that you want to study, has a lot of symmetries. When you embed it onto a QPU, because of some errors in the QPU and non-uniformities in the qubits, different qubits will not behave in an identical manner. And calibration refinement is an attempt to kind of nudge the system in a direction that makes sure that the symmetries of the original problem are satisfied. So I would encourage you to look at this tutorial paper, which is really nicely written, and we made good use uh, of the material in here. And shown on the right is what calibration refinement looks like. So we are changing two different quantities. There's a quantity called flux bias offset at each individual qubit. And we can also change the values of the coupler strengths, so J, Ij values. We change them ever so slightly so that the symmetries from the output from DWave matches the symmetries of the original problem. So on the right hand side here, I'm showing a plot that we got for a particular grid point in the S and J inverse grid. And on the top, I'm showing how the flux bias offsets evolve with iterations. So we did 1,000 iterations, and how the coupler strengths also evolved with time. So we did something very similar to a gradient descent type of an approach. It's based on this tutorial here. Okay. So let me move ahead because there are a lot of details in this calibration refinement procedure, which might obscure the message that we have. So how do you find the locations of the boundaries between two different phases? So for a second order phase transition, which is what we were interested in, there is a quantity called the binder cumulant. So it's a fourth order statistic of the magnetization of the samples that you get. And the key idea is this. Let's say you have access only to two different system sizes, or maybe four or five, but none of them is infinite in size. Then you can plot this quantity called the binder cumulant as a function of whatever parameters you want to vary. And it turns out that they are all going to have the same value at a critical point. So this is the method that we used. So we used many different system sizes, about 8, I think. And I'm showing here at s equal to 0, the s equal to 0 line, there is a phase transition at a particular temperature. And we plotted the binder cumulant, and we really did see that as you change the system size, the curves are all different, but at a particular point they all cross, except possibly this yellow line. And this really tells you that this matches this should match the critical temperature. This value of J inverse should match the critical temperature for S equal to 0. So we did this for a bunch of different values of S, and we got the binder cumulants to cross. And we were able to extract a boundary between the different phases. And this also tells you, it also gives you a map. So if you want a particular temperature, that corresponds to a particular value of J inverse. So if you want to simulate T if equal to 2.2, you can use this line and figure out what value of J inverse you should be coding into your device and sending to the LEAP cloud access to get samples at that temperature. So we did this for many values of S, and you can also do this for the other region, for S greater than 1 region. We didn't do this, but in principle is the same procedure. Okay. So next, again, there are a lot of details here, so I'll skip a lot of them. But the final objective that we had was to find the so-called critical exponents. So let me just really quickly tell you what these are. So there are a few different physical quantities, things like magnetization susceptibility or heat capacity and so on. And when you're really close to a critical point, the functional form of these quantities is very peculiar. So the magnetization susceptibility, it scales as the distance from the critical point raised to minus gamma. And minus gamma turns out to be a positive quantity, which means that the susceptibility really blows up. It becomes infinity for an infinite sized system. And finding gamma is really important from a physics perspective. So all of these exponents, gamma, alpha, nu, and beta, are important from a physics perspective. So the values for the S equal to 0 line, which corresponds to the 2D square latticizing model, those are exactly known from a century ago, essentially. Their values are exactly known. But to find the values of the remaining, oops, a plot was missing. Yeah. So we did classical simulations to find those exponents for other values of S, and it turns out they remain the same. So these exponents, we know their values exactly, essentially. So even if you change S value between 0 to 1, the answer should turn out to be nu equal to 1, gamma equal to 1.75, and so on. Now, we wanted to get these values from the quantum annealing samples, and that's what I'm going to describe next. So how do you get something like magnetization susceptibility or heat capacity from samples? So it turns out there's a really simple relationship from basic statistical physics, which tells you that magnetization susceptibility is proportional to the variance of the magnetization of the samples that you get. And same thing with the heat capacity. It's just proportional to the variance of the energies of the samples that you get. So these are quantities that you can readily compute from the samples that you get from DWave. So that's what we did. So for a variety of system sizes, we plotted the heat capacity, the susceptibility divided by beta, because we can't get rid of the beta for some technical reasons. And same thing with CV divided by beta squared. And what we found is really consistent with what you would get from an exact solution perspective, or if you did Monte Carlo simulations on a classical computer on your laptop or an HPC. As you make the system size bigger, the curves should become more and more peaked, which is indeed what you see. And the peaks should shift towards lower temperature, which corresponds to lower J inverse values. So I'm just showing here some stars which are numerically extracted peak values of these curves. And the key point here is that by looking at the locations of these peaks and the heights of these peaks, you can really extract some of the critical exponents. So this is what we did next. So I'm going to skip some of the details, but for those of you who are interested, there is this really well-known ansatz called the finite-size scaling ansatz, which you can use. And there are lots of details here. And I'm just going to show you the final plot. Okay, so the ratio of the exponents gamma and nu that we found using two different methods are these. So the blue dots are blue triangles are really kind of our bad estimates, and our better estimates are the black dots. And the exact answer is 1.75. So you see that what we got is off. It's not 1.75. It's off by 15% to 20%, depending on the value of S. But after we put out this manuscript, we actually were able to do better calibration refinement, and we have better exponents now, which are really close to 1.75. We haven't put this in yet, and in the next version of our archive manuscript, we will be updating this plot. But really, what was important here was to do the calibration refinement really well, and that was a really difficult task for us. So we could say that we have had a decent amount of success, although we would like to get exactly 1.75, which you can do with classical Monte Carlo. So this brings me to the last part of the talk, which is why do you want to do this at all? So if you have done a course in statistical physics, then you might be familiar with Markov chain Monte Carlo techniques, which are typically used for solving problems of this type on your laptop or on an HPC. And it turns out you can go to really big system sizes, like 1,000 by 1,000, or even bigger if you are really smart. And this is really important because the critical exponent values that you will get will become better and better the larger your system size is. So the largest system size we actually embedded on DWave was 12 by 12, which is fairly small compared to 1,000 by 1,000. So one question someone might ask, and we ask this question as well, is why should we use quantum annealing for this problem at all? And it turns out there's a really nice answer for this. So there is a property called, or a problem, let's say, an issue called critical slowing down, which which usually occurs with Monte Carlo simulations, so classical algorithms. But we found that this problem doesn't exist with a quantum annealer. So let's quickly look at what this problem is. I want to give you a high-level picture of what this problem is. So imagine that you are using your laptop to simulate this model or any other model like this. So you code up a Markov chain Monte Carlo algorithm, you get samples, but it turns out that the quality of the samples reduces if you have frustration, usually, but not always. And very close to a critical point, this algorithm has a problem of convergence. It really takes a lot of time in order to get statistically independent samples. So the samples that you get are correlated with each other. Sample number 2 is similar to sample number 1 to a large extent. And only after doing, let's say, 1,000 samples or even bigger number of samples will you get samples that are sufficiently different from each other, which is important in order to get the critical exponents and get the critical points correctly. So this problem really and this is really a problem when t goes to 0. So t measures the distance from a critical point, and when the system size is made bigger and bigger. Now, let me say that it is actually possible to overcome this problem to some extent for some models. So people are really smart and they're able to come up with really smart techniques to avoid this issue. But in general, there is no recipe to evade this problem for any model that's thrown at you. Now, there are many ways of assessing critical slowing down. There's one called autocorrelation function. This is a really complicated formula, so I'm going to skip it. And I'm going to show you the results from DWave and from a Monte Carlo simulation. So the black dots here show you so on the horizontal axis is time in some units. And the black dots tell you show you the samples that you get from a very simple Monte Carlo algorithm that I ran on my laptop. And the red triangles here correspond to the data from DWave's quantum annealer. So what does this plot tell you? So it tells you that to get really statistically independent samples, so you want this autocorrelation function to be close to 0 if you want for statistically independent samples. So this tells you that I kind of need to wait 100 time steps in order to get statistically independent samples from a Monte Carlo simulation on a laptop. But when you do the same thing with DWave, you find that they are pretty much always statistically independent. You don't need to wait. So every single shot, every single measurement that you get from DWave is statistically independent from the previous one. Now, this is really not surprising. It comes from the design of quantum annealers. So what do? you run the same program, let's say 100 times or 1,000 times. But measurement number two really is not in principle correlated to measurement number one, because after the measurement of the first anneal, you reset the qubits to the all up in the x direction, you do the anneal, and then you measure in the z basis. Um, so this is not surprising in some sense, but we just wanted to have concrete evidence to show that really isn't a problem. So let me put a caveat here. This is for a really small system size because we couldn't do quantum annealing yet for, let's say, 1,000 by 1,000 system size. But this is really going to be a key factor as one increases the system size. This shows you that, or at least it promises, um, it holds promise for a large system size for a problem that whose solution you don't really know. It might eventually turn out to be a better idea to use a quantum annealer as opposed to a classical Monte Carlo method, or maybe there's some hybrid that would end up being good. Okay, so let me end the talk with some conclusions. So the key takeaway is that you can use a quantum annealer and you can use it to map out the phase diagram at finite temperatures as well as at different parameter values of some classical magnetic material model. You can identify critical points and exponents. I showed that we had some decent success with it, but we have improved results which show you can get very close to the actual answer. Another point is that even though quantum annealers are not ideal Gibbs or Boltzmann samplers, we only require up to the fourth order moments from the distribution. We don't need the sampling to be exactly Boltzmann type. It's okay even if there are deviations as observed in the literature, but you can still do a good job using a quantum annealer. And a key point here, which is kind of forward looking, is we might be able to evade this important issue called critical slowing down if we were to use a quantum annealer. And that tells you that maybe you can have a benefit or advantage over classical Monte Carlo algorithms. And let me also mention that roughly 2 months after we posted our manuscript, a bunch of researchers from Europe and Israel, they put out their own manuscript on a very similar problem. And they were also able to refine our procedure to some extent to get somewhat better results as well. So I encourage you to check out their work because it's also fairly interesting. So let me stop here. I would like to thank Los Alamos National Lab for funding support and all of my collaborators for helping out. And thank you for your attention.
Great. Thank you so much, Pratik. Our excellent panelists spent a lot of time answering questions, so we have just a few left for you. The first question is, I'm exploring the potential of quantum computing for problems that involve continuous state and action spaces, particularly where classical methods struggle with scalability or computational efficiency. I'd be really interested to hear your thoughts on whether current quantum techniques, such as variational algorithms, quantum annealing, or others, are suited to problems of this nature. Are there any approaches or developments in the field that you think show promise for handling continuous domains?
That is a really good question. I should start with a disclaimer that I'm not very familiar with problems with continuous variables. If there is a way to discretize your problem, maybe it could it could be studied using a quantum annealer. But I'm sorry, I'm really not well equipped to answer this question.
Okay. Someone thought that the image and the phase transition slide was beautiful. If you want to bring that up and ask what it was.
Yeah, this was so I really spent a lot of time trying to make these figures. Also, Francesco, he came up with these ideas. But thank you. Maybe it was this figure or these two figures. But yeah, this really we really had to do a fine grid of S and J inverse values, and we had to do this calibration refinement technique. And so this plot really required a lot of effort and compute time because getting these curves was really difficult. So Francesco wants to say something, I think.
There's a question. Sorry.
Yeah, question was about the picture that you had when you were talking criticality. It was this fluid flow, chaotic fluid flow that you had in That
Oh,
one.
it was not this one. Okay. Well, which one?
Go
It
back.
was much earlier, but maybe who asked
The
me
water
can
ice
find
phase
the
diagram, or
Much.
oh, this one.
the-
Oh, this figure. Oh, yeah. Unfortunately, I can't take credit for this. Microsoft PowerPoint came up with this.
Okay, next
But
question.
yeah.
In the antiferromagnetic phase, you have a blue, i.e. 0 region close to J, superset 1 equals 0, which seems to expand towards S equals 1.5. Would you have an explanation for that? It's a deviation from the exact solution, I believe.
Yes. So that is actually a really good question. So if you look at J inverse going to close to 0, the maximum was, I think, 1 that we were able to do. If you look at this region, this should really be yellow. It should all be 1, but it's much less, like 0.1 or something. And so the problem here is that the annealer wasn't able to, or we weren't able to make the annealer get to the ground state. So the ground state manifold is really highly degenerate. And this is a point where being a Boltzmann sampler is kind of, being a good Boltzmann sampler is key. So there is a region here where the quantum annealer wasn't able to get the quote unquote correct answer. But the thing is, if you did the same type of calculation with a classical Markov chain Monte Carlo type approach, unless you are really smart with your algorithms, you are going to face the same problem. And this is something we are actually studying. So this region where S is greater than 1 and where the temperature is really low is there's a physical barrier to getting. There's a physics-based barrier to really getting to the ground state, and we are exploring that in a follow-up project.
Okay, last question. What was the most challenging part from your experience to use quantum annealing compared with classical approach?
Sorry, could you repeat that? I got distracted by the chat.
What's the most challenging part from your experience to use quantum annealing compared with a classical approach?
So for me, the most challenging part was the calibration refinement. And really, if you don't face this problem when you type up a code for your laptop, because every bit is going to behave in the same manner. So if you have variables or spin variables stored in some data structure like a list, they really are going to behave in the same manner. It doesn't matter which one comes first, which one comes later on. But because this is physical hardware, and because hardware is complicated and difficult to manufacture, there are differences between one qubit number 300 and qubit number 344. And if you want really good results for something that is sensitive to this type of noise, which includes finding critical exponents, you want to get rid of these non-uniformities as much as possible. And for this particular problem, this turned out to be a big challenge. I had to learn a lot, and I had to come up with kind of build up on the tutorial here with Andrew King's help. But I think in the end, we got a decent result. That was really challenging.
Well, thank you so much. From the many people who asked, this webinar has been recorded. It will be up on the DWave YouTube channel later this afternoon. We will send out an email to everyone with a link to it. And Pratik, are we able to share the slides as well?
Yes.
Then we'll send a link to the slides as well. So thank you so much to our presenter and to our panelists and to everyone who came today. We appreciate your time. Bye-bye.
Thank you.